so this is 141. We're going to talk about RSA today, and I intended to move this 403 to next week. Let's see if a refresh will do that. All right, I probably need to upload the new version. Just a moment. I did change it, or I thought I changed it, because I'm not going to demonstrate it until today because something was wrong with it. And I thought I changed it, but perhaps I didn't upload the latest version. Let's see if this does it. All right. Yeah, that's right. So it'll be due next week, 403. Got to look at it today. All right, so let's take a look at the slides and talk about RSA, which is the venerable primary version of public key encryption that started the whole thing. The basis of the RSA company and the main one used for internet traffic. It is gradually going away, being replaced by elliptic curve cryptography, and both of them are now going away, to be replaced by these post-quantum things, although that process is only in its infancy. So we'll talk about the math behind RSA and other topics about it here. So here's the math. You have to understand what a group is. We talked about this before, but here's how it goes. The group Zn is integers modulo n. Now, in order to be a group, a set of numbers has to have this property. And by the way, they don't really have to be numbers, but we're only going to use numbers, so that'll do for tonight. You have to have an identity element, like 1, and each member must have an inverse. So you can't have a 0, because 0 times something, there's nothing you can multiply by to get back to the original something. 0 destroys information. So Z star 4 contains 1 and 3 because it will only contain numbers up to n minus 1. You exclude 0, and you also exclude 2 because 2 has no inverse. If you multiply 2 times something, modulo 4, you just hop between 0 and 2 and 0 and 2. You can never get back. And that's generally the case if you have a number that is a divides into the group number here, the n, evenly. You can't use that number. It's not part of the group because there is no inverse for it. It's going to come back to us. This is why we have phi of n. So the group ends, if n is prime, then the group will contain all the numbers up to p minus 1 because there is no issue of any of these numbers evenly dividing into n if n is prime. So that's nice. The only thing missing is 0. All right. So, but if you consider this kind of group, which is the kind we're going to use for RSA, where n is the product of 2 primes, this is 2 times 5, then you have this strange result where the Z star 10 contains 1, 3, 7, and 9, only 4 elements, because 0 is excluded, as we said, because it has no inverse. 2 and all multiples of 2, 4, 6, and 8, are excluded because they will only hit even numbers as you multiply them by things. They will never hit the odd numbers. They won't hit all the numbers, and there will be no way to reverse them. And 5 is excluded because it's evenly multiplying into the 10. So that's the game. You exclude ones either because they have no inverse or because they have a common factor with 10. So 2 times 3 is no good because this is 2 times 5. The common factor of 2 means it will not be acceptable in the group. And so they have all the numbers you retain must be co-prime with 10, which means they have no common factor with 10. So 9 is included, even though 9 is 3 times 3, because 9 is 3 times 3, and 10 is 2 times 5, so it has no common factors with 10. So this might seem a little complicated to understand, but it turns out to be very easy to get the number of elements in these groups. Euler's totient does it. It's very simple. If n is the product of a certain number of prime numbers, then you take p1 minus 1, p2 minus 2, and so on. That's how many there are in the group. And you can kind of see it, obviously. You take each of the prime factors, and you exclude that and all multiples of it. So anyway, for Z star 10, it's easy enough to see. It's 2 times 5, so Euler's totient is 1 times 4. That gives you the 4 elements in Z star 10. So, all right. So here's the parameters. N is the modulus. which is the product of P and Q, two prime numbers. E is the public exponent, and in practice you usually always just use this number. And so a public key is N and E. Anybody can encrypt data with N and E. They can only decrypt it with a private key, which is derived from P. So P is secret, and various other numbers derived from P are secret also. So here's the trapdoor permutation. You take the plaintext message, raise it to the E mod N, and that is the ciphertext Y, which you can now transmit over an unsafe medium, because nobody can open it unless they have the decryption key D, and they decrypt it with the same process. They take the ciphertext to the D mod N, and that gets you back to the original plaintext. And you can't get D without knowing P and Q, which are the secrets, and that's what the security of the system relies upon, that you cannot take N and derive P and Q from it, which is the factoring problem, which has been hard and known to be hard for thousands of years. In practice, although never proven to be absolutely mathematically hard, as I was talking about last time, there's no known way to do it quickly. To calculate D, you need D times E to be 1 mod phi. And that means if you do the decryption, X is Y to the D mod N, which is X to the E, that's what Y is, to the D mod N, that's X to the ED mod N. Now, E and D are 1 mod phi. And it turns out that means this turns out to be just 1 up here. And the part that is not immediately obvious is why would mod phi matter here in the exponent, but it's mod N over here. And that is because phi is the number of actual values you can use in the group. That's the actual number of elements in the group. And so taking anything to this large number of powers will loop around enough times to take you back where you started, because ED is 1 mod phi, and phi is the actual number of elements in the group. So that's what's here. This is also called Fermat's-Little theorem. It was stated in 1640. It wasn't proven for about a century, but it is known now, and that's the secret. Any number to the phi is 1 mod n, and that's the relationship between phi and n. So if you do this with n equals 10, then 10 is 2 times 5, so p is 2 and q is 5. Phi is therefore 4. There are 4 elements in the group. Now 3 is a generator of the group, and you can see it. Remember, the group here contains just these numbers, 1, 3, well, we're going to see. We're going to start with 3. We start with 3. 3 to the 1 is 3. 3 to the 2 is 9. And n is 10, so that's fine. 3 to the 3 is 27, so that's 7, mod 10. 3 to the 4th is 81, so that takes us to 1. So here is the group, 1, 3, 7, and 9. That's the group. And if you multiply it by 3 again, you'll just loop around here. So you've generated all possible elements of the group by taking 3 to a power. And that's what you need for RSA encryption. Your message is a number, and you're going to raise it to a power, getting another member of the group, and then you're going to raise that to another power to get back to the original message. That's how it works. All right, so if you take powers of 3, 3 to the 1, 2, 3, 4, gives you 3, 9, 7, 1, and back to 3. 3 is a generator of the group. And this repeats with a cycle of 4, which is phi, not 10, which is n. So you encrypt by raising x to the power of e, forming y. X is the plain text, y is the ciphertext. You decrypt by raising that to the power d, which gets you back to the plain text value. So if you consider all right, this seems to simply repeat the same information. P is 2 and Q is 5. Here's phi. Here's ED is 1. So this is where we're going to find D. Okay, so we want ED. We know that E is 3. We specified that. And this is the public key, N and E. So we're going to have to find the decryption key. So you take 3 times various numbers, and we find that 3 times 3 mod 4 is 1. So the decryption key is also 3. So to encrypt a message, if you have a plain text message and you make it 3, for example, to encrypt it, you take 3 to the 3 mod 10, and that's 7. And to decrypt it, you take 7 to the 3 mod 10, and that's 3. So it works. Of course, in this small group with only 4 elements, the numbers are really small, but that shows you how it works. Let's try another one with a larger value of n equals 14, which is 2 times 7. So if I take a generator of 3, I can take 3 to the 1, 3 to the 2, that takes me 9 again. 3 to the 3 is 27, mod 14, that's 13. 3 to the 4 is 81, which gives me 11. 3 to the 5 and 3 to the 6 give me more values here. So you end up with this, 3, 9, 13, 11, 5, 1. And that is the 6 elements in here. Since this is 14 is 2 times 7, phi is 1 times 6, so there are 6 elements in the group, and there they are. And you generate all 6 of them by raising any of them. They're all generators. You can take any one of them and raise it to powers, and it will loop through all the other values. 3 is a generator of the group. All right, so now we're going to find D. So we have, here's the N is 14, and E is 5. So we're going to take 5 to various power, multiply 5 by various numbers, mod 6, which is phi. So 5 times 1, and so on. You find that 5 times 5 mod 6 is 25, mod 6, which is 24 plus 1, so that's 1. So 5 is the decryption key. So if E is 5, D is also 5. So now we can encrypt a message like 3. We take 3 to the 5th, mod 14, you get 5. And when you take 5 to the 5th, mod 14, you get back to 3. So it works just fine, as you can see. All right, so in practice, here's what you have to do. The key generation procedure is actually quite burdensome. Project NCL. All right, I'll have to turn that on. Let me make a note of that. Enable NCL. Good. And you could also just turn it in by sending a message inside Canvas in 121. All right, so so you have to find 2 random primes. Then you multiply 5 from them, p minus 1 times q minus 1. Then you pick E, and then you calculate D from E. This is the process. So you can do that in Python 3 with some fairly simple commands. And I think we've done that in the project, using PyCryptoDome, which is the most modern library for this. And you see how long it takes. To generate a key takes 0.15 seconds with length of 1024. To encrypt is very fast. You see, it only took 0.02 seconds to do 400 encryptions. To decrypt is slower, 0.01 seconds to do 5 decryptions. And you can see the encryption is fastest, decryption is much slower, key generation is very much slower. And that's because you have to hunt for those random primes, and you may have to guess a lot of times to find a prime number. All right, so here's a way to do it with various lengths, and I tried doing various key lengths here. See, 2048 took less than a second, 4096 generating a key took 1 second, but then 81 seconds, 1400 seconds again. See, it gets to be really slow. Why decryption number is 5, not 400? Well, I just chose a number just so I could see. I could have put 400, then it would have took longer, that's all. I just varied the number to get, so it doesn't matter. It's linear, so if I did more decryptions, it would just take more time linearly. Good, these are good questions. All right, there's no special reason, no meaning there. So, all right, so now, as you can see, encryption is pretty fast, generating a key is pretty slow, so you could just encrypt all your data with RSA, but in practice, people don't bother with that. They use AES. Typically, all you do with RSA is encrypt an AES private key and send that to the other end, and then you use AES from then on, because AES is really fast and efficient. And all you really need public key encryption for is to move the secret key over. So now there's textbook RSA, where you would just take the plain text and convert it to, say, ASCII bytes, and then interpret that as a number. That would be your X. You can do it that way, and that's the way I did it in those examples with small numbers in the projects. But that has a flaw. If you were to encrypt 2 plain text messages and then multiply them together, I could take the ciphertext and multiply this together, and I could generate a valid ciphertext which would match a valid plaintext by multiplying the two numbers together. So that's not good. I can appear to know the key when I don't know the key. I can take two ciphertexts, multiply them together, and submit them as an encrypted message, and they will decrypt to some sort of valid message. So that's a forgery attack, and that's not a good property for a cipher system. So the recommended solution is this thing, optimal asymmetric encryption padding. You run it the symmetric key is what you're trying to send. You run it through a padding algorithm. That makes it as big, that makes it as long as n bits, and then you send that. The padding is a pretty complicated procedure. I think we got it here. Yeah, it is pretty complicated. You mix together these various things. You've got some randomly generated strings and so on, but this is considered quite secure, the OAEP algorithm, to pad things to send them by RSA. There was an earlier system that unfortunately is still used by a lot, where you just have a 0 and a 2, and then a random number, and then a 0, and then the message to pad it. This turned out to be very insecure. There were a whole series of attacks against it. It's still used in legacy, but is considered to be a very poor choice compared to the more modern OAEP. All right, so that is encryption with RSA, to transmit a secret over a network. Now we're going to talk about signing. You can sign a message X with X to the D mod N. So you use your decryption key, not the encryption key, but nobody else knows D, so anybody can verify it using E. If they take the signature to the E mod N, they'll get the original plaintext. So it's a signature. X is not secret, that's the message you sent. So this is a way to sign a message. It does not provide confidentiality, just a signature, but it's a classic RSA signature. Now, typically, you don't want to sign the whole message because it's long and this calculation would be long, so you hash the message and then sign the hash. So the textbook RSA signature, if you actually take the plaintext message and raise it to the D mod N, then attackers can easily forge signatures. For certain messages like 0, but the plaintext is 0 or 1 or n minus 1, then it doesn't matter what power it's raised to. And so that's one solution. Also, if you have two of them, you can multiply them together. This is called there's a generalization of this as the blinding attack. So if I want to get the signature for a message M, which this user would never sign, if I can find a value R, so that R to the E mod M is a message they will sign, I can take that signature and I can deduce the signature for the other message from it. So the naked RSA signatures, where you just take the raw message and raise it to a power, are pretty dangerous. They have a lot of defects cryptographically. And I've done some CTFs where you actually have a challenge to remember there was one where you had a system where you could send up a number and it would sign it, and you could do maybe a few hundred of those before it would refuse to sign anymore, and from that you had to predict the signature for another one. And it turned out that even if you know the first 100 prime numbers, you can predict an awful lot of the numbers after that. So anyway, so there's a better standard here, the probabilistic signature standard. This is the recommended one, like OAEP, makes encryption more secure. And what this does is it takes the hash and mixes it with a padding algorithm that combines it with random and fixed bits again, so that you can't just take two messages and combine them together there to make what you'd get to sign. There used to be a simpler scheme that came earlier, where you just take the hash and run that through X to the E mod N. That was just using the full domain hash technique. We just hashed the message. And that is considered to be less secure than the probabilistic signature scheme. Although in practice, they both work, as you would think. I mean, the point is, if you're trying to do this forgery up here, the simplest one is just combine two messages. If they've been hashed, combining two messages is not the same thing as combining two hashes. So as long as the hash value is something reasonable, like SHA-1, you're probably fine. That's why I say in practice, it's fine. The only thing wrong with the hash scheme is it might be fall to fault attacks, which are attacks basically against the hardware, where you lower the power supply or cause a defect during the calculation. We've talked about those before. All right. So, implementations. In practice, you should always use libraries, standard libraries to do crypto. You should never write your own crypto. That's always a mistake. You're likely to make a mistake. It's much better to just use standard libraries. However, there is one interesting issue here. If you want to consider RSA with a 1024-bit key, you'll have to calculate something. You'll have to raise a number to a number here, which is going to be like 1024 bits long. And that would be 1024 multiplications, which is impossible. We talked about this. You can't even do 2 to the 100 calculations on any computer anywhere. So it would seem like you couldn't do RSA at all, but that's because you don't do it by doing multiplications one at a time. What you do is you take the input and square it, then you take that output and square it, then you take that output and square it. So you, with a very small number of calculations, you get these values, and then you combine them to make any exponent. So you end up only having to do the logarithm of the number of calculations. This is just an algorithm that gets you there faster. And that's what you have to do, or you'd never be able to do any such large exponentiations. So that's the point. A 1024-bit exponent can be calculated with only 1,500 multiplications. Each number being multiplied is still pretty big, but it's possible, as opposed to the other way, doing them one by one. You'd never get there at all. Now, this means, however, that exponent bits of 1 take more time than exponent bits of 0. You're multiplying a lot of numbers together, so if there's a 1024 in it, you include that. If there's a 512 in it, you include that. If there's no 512 in it, you don't include that, and you save time by moving forward. So that means the encryption will be faster for some values of the exponent than others, and if you measure power consumption and your timing, it can leak out information about the key. This is not easy to prevent. There are some libraries like this one from Microsoft. This one claims to be immune to these timing attacks. Evercrypt. That's a concern. All right, another thing you might worry about is the way you typically use RSA is for HTTPS. So you have a web server on a powerful server, and you have a bunch of clients that are on weak devices like cell phones. And so you would like the client computing job to be small, so they can do it quickly on this small device, and it's okay if the server has to work harder. So that's why you typically choose a small e, because what the client is doing is encrypting data to send it to the server. So they're taking plain text like their password and raising it to the e, and that the higher this number is, the more calculations you have to do. So if you use a small e like 65537, then the client has a simple task. Of course, if e is small, then d is big, so that means more work for the server, but that is the choice that is typically made. All right, there's also something that saves you a little bit of time. There is something called the Chinese remainder theorem, where if you're trying to calculate x to the e mod n, you can break it up into separate moduluses of p and q, which are smaller, making RSA 4 times faster to calculate. So that's a useful fact in the algorithms. And so, things that can go wrong, turns out there's a lot of things that can go wrong that we'll talk about later. But fault injection, if you alter the power supply or hit chips with a laser pulse or a cosmic ray, then that can break deterministic schemes, but it can't break schemes including randomness, which is why these padding schemes that include randomness are considered to be superior. So let's take a look at a Kahoot. All right. Good. Well, we may have only 2. We'll go on just so people can see the questions, but there won't be much competition. All right, how many elements are in the group Z star 15? "15 is 3 times 5, so the number of elements in the group is 3 minus 1 times 5 minus 1, which is 2 times 4, which is 8. That's 5. The number of entries in the group is 5, which is P minus 1 times Q minus 1. And here P is 3 and Q is 5. Let's try another. What's Euler's tangent for N35? No answer. Well, all right, let me try and explain this. I did not anticipate this. All right, 35, let me make this bigger. 35 is 5 times 7. So P is 5, Q is 7, and P minus 1 times Q minus 1 is 4 times 6, which is 24. So that's how you do it. That's Euler's tangent, which is the number of elements in the group. All right. What saves time on the client side? Yellow E, good. All right. All right, what's the slowest operation? Yep, key generation. All right. So, it's, Oh, I see. That's why it was empty, because there are only 2 players. Right, okay. So Joseph and Richie. All right.